Alright guys, so today we will be covering section 10.5 on your textbook, which is area and the arc length in polar coordinates. We will begin first by talking about the area of a sector. Okay, so to develop the development of a formula for area of a polar region uses sectors of a circle rather than rectangles. So remember when we were doing back in, what was it, chapter 5-ish or whatever it was, we first talked about Riemann sums, and we talked about how we can split up a graph into multiple rectangles of different widths, etc. Well, with polar, we're not going to use rectangles. We're going to use sectors. So we're going to go back to geometry for a moment. So here's a refresher for you. The area of a sector is equal to 1/2 times the radius squared times the angle. In this case, the angle has to be in radians. So just keep that in mind. We're not using rectangles for this. We are using small sectors of a circle. Okay? So consider the following graph. So you have, for example, I don't know, I made this random curve here, and I'm trying to figure out the area from alpha to beta. So right here, this striped zone. And the formula or the function for this is r equals f of theta. To find the area of this region, we're going to partition into n equal parts. So that's my drawing here at the bottom. So do your best. I try to do a whole bunch of sectors here. And just like with Riemann sums, remember that to find the width of each rectangle, you would take basically the lower limit, the upper limit, and divide it by the number that you had, right? Well, we're doing the same thing. If you take your upper limit minus your lower limit and divide it by n, that's going to give you the width of each one of your sectors. You want to keep your sectors to be exactly the same, okay? So this is kind of like a review on Riemann sums, like in very, very quickly, okay? So then we can say that the area of this is going to be approximately the summation of each sector starting from 1 to n, however many sectors that we have, of 1/2, right? This represents this 1/2 over here that we're talking about on the area of a sector, here in this case. And then the theta is going to represent right here by the width of each one of your partitions here, right? So basically this is just the formula, 1/2 r squared theta. 1/2, here is your angle, here is your radius. Cool? We simplified things out. We take the limit. It literally boils down to the following formula, which is really what you need to memorize. So you don't need to know how the formula came about, but here's how the formula came about. Area of a sector, here in this case it is a sector because we're doing polar graphs and we're using sectors instead of rectangles. It's going to be the integral from alpha to beta of f of theta squared d theta. If you're watching the video, I would go ahead and pause it at this moment and make sure that you were able to copy down everything that I have, and then just press play when you are ready to move on. Alright, we're going to go ahead and find the area of one of this, try an example. So we're going to find the area of only one petal, okay, one of the petals, it doesn't matter which one of the petals of the following rows. Now, if you watched the previous videos, I'm sorry if you didn't, you're going to have to go back and watch it. I picked this on purpose so that we already know what the sketch looks like, so that we can kind of move on. But very quickly, I'm going to redraw it just in case you did not watch the last video. This is going to be a rose with 3 petals. I think I just changed the number to a 3. I think the previous example was a 2. That just means the length of each petal is going to be 3. So it's going to be here, and then it was somewhere here and somewhere down here, right? So the petals, here's what the sketch looks like. Right? Now, here's the reason why I encourage you, and I'm almost saying like you must sketch things out when you're doing this. It's for the following. I believe that one of this, finding the area of one of these petals will be easier versus the other. In my opinion, it would be this one. Here's the reason why. If you recall from our last example, we knew where the tangent lines at the pole were located. You guys recall that? There was one tangent line located right here at pi over 6. Agreed? And then there was another tangent line located right here at, technically we could call it 5 pi over 6, but for our purposes, could I also call it negative pi over 6? You guys follow me? Why would I care about that? Because now I have my boundaries for my integral. So that means that the area of this thing is going to be equal to 1/2 the integral from negative pi over 6 to positive pi over 6 of what? The function squared. So this function right here, 3 d theta. You guys with me? Okay, so then the area would equal to 1/2 from negative pi over 6 to pi over 6 of 3 squared is 9. But can I go ahead and pull out that 9? You guys with me? So can I have it to be 9 over 2 then? And then cosine 3 theta squared will be just cosine 3 theta squared d theta, right? Uh-oh. I need to integrate this thing. So now we're going back to basically chapter 8. Can you or do you remember your integration rules to help you out here? You're going to have to use, and in case you forgot, power reducing. Your power reducing formulas. Okay? So that means I'm gonna need more space. So area equals 9 over 2 from negative pi over 6 to pi over 6 of. Do you guys remember how to power reduce cosine squared? It's going to be 1 plus cosine of 2 twice whatever angles you had here. So 2 times 3 theta is going to be 6 theta over what? 2 d theta, right? Now at this point, you're pretty much set to begin integrating this out. You could, if you wanted to, you could break this up into 2 different fractions. So like area equals 9 over 2 from negative pi over 6 to pi over 6 of 1/2 plus 1/2 cosine 6 theta d theta. Agreed? Like that's the same thing. Okay. Area equals 9 over 2, and I'm going to begin integrating. The integral of 1/2 becomes what? Just 1/2 theta, right? Plus the integral of 1/2 cosine 6 theta. Well, if you need to do this, you don't have to do it, but if you need to, you can let u equal 6 theta. Therefore, du equals 6 d theta, right? Which means that du over 6 equals d theta, right? And then you can have the 1/2 and the 1/6 being multiplied together, right? And what is the antiderivative of cosine? Sine. So plus 1/2 sine 6 theta. Right? From where to where? Right? How can you check that this is correct? Hold on, I'm like starting it out. The derivative of sine is cosine, and the derivative of 6 is, this should be 1 over 12, right? Sorry, I was like, wait a second, yep. Yeah, because we had the 1/6, I'm sorry, 1/6 times 1/2 is 1/12, right? My mistake, I'm sorry. Just trying to rush there. Are we good now? Yeah, right, because cosine and then 6 times 1, yep, alright, so we're good now. Alright, so then 9 over 2 times, alright, so we're going to plug in pi over 6. 1/2 times pi over 6 is pi over 12, plus 1/12 times, alright, 6 times pi over 6 is just pi, right? sine of pi is 0 minus 1/2 times negative pi over 6 becomes negative pi over 12, right? Plus, and then again this is just going to go to 0, right? Area is equal to 9 over 2. Pi over 12 plus another pi over 12, so that's 2 pi over 12, which is pi over 6. So that goes down to be 3 pi over 2. I mean 3 pi over 4, right? Sorry. Oh, I don't know where my white end's out. 3 pi over 4 units squared. And that right there will be how to find area in polar mode. In other words, you need to know where your asymptotes are located to be able to have your boundaries here. Okay. In general, finding the actual area of it, the formula of it, it's relatively simple. It's just take your function and square it. The difficult part here is finding out your boundaries here. And then, do you remember how to factor? I mean, not how to factor, how to integrate. Okay? So, the more integration you know, the easier this is. The less integration techniques you remember, the harder this is going to become. Next class, we'll finish up the lesson with how to find the arc length in polar mode, and we'll review for a test.